The first lecture will be given by Professor Huppert from Cambridge.
Okay, well, I'd like to talk about Stokes drift in an ocean above a coral layer and tell you about some of the ideas, the field conformation and the biological implications. Next slide, please. There'll be some background material, then I'll tell you about the fluid dynamics, tell you something about the field data and the conclusions. Next slide, please. Now, there are waves in all different forms, as you see here, across the ocean. And the ocean covers something like 70% of the Earth's surface. So it really is very important. They can be of different sizes. The next slide. As far as you can, this is a big wave about to break, and this is me surfing the wave right now, I could say, because you don't know any different, at Bondi Beach in Australia. Next slide, please. Waves have a dispersion relationship that link the frequency omega with the wave number k, which is inversely proportional to the wavelength. The phase velocity, which is the speed of any of the phases, like the top of the wave, and that square box there's an equal sign, is given by omega over k, and you see the formula there. And when the depth of the ocean D is very much larger than the wavelength, you get this expression g over k to the half. While that's the speed at which the phases go, independent of the amplitude, as long as it's not a breaking wave, as I showed you before, the energy goes at a different speed. That's the group velocity. And it happens, as you see in this limit, to be a half the phase velocity. So the amplitude, the top amplitude, if you like, or the bottom amplitude, goes at twice the speed of the energy. What that means is, if you initiate a wave packet, the front of the packet will go at the phase velocity, but it doesn't have energy to keep up with it. So it dies down, and what was the second wave takes over at the front, and then it dies down, and then the third wave. Next slide, please. But now there is another important velocity that was initiated by Stokes, whose 200th birthday we celebrated just a few months ago, and was the Lucasian professor, the position that Stephen Hawking held until recently, for 54 years. Next slide, please. And Stokes showed that there was a drift, or an important velocity, that goes like the square of the amplitude. So very important how big the wave is. That decreases exponentially with depth, as you see, e to the z over lambda. It's purely horizontal. It's second order in amplitude, and it decays exponentially with depth. But it's very, very important. Much, much slower than either of the phase or group velocity. And the next slide shows you one of the consequences, which is this Stokes drift that brings up wood and plastics and all sorts of garbage onto the shore. Next slide, please. Now, what I want to talk about today is an extension of that, which is, if you like, from a fluid mechanical point of view, what happens if you have an inviscid ocean, water, and below it is a porous medium. The porosity is so small, the little bits are so close to each other that viscous effects play an enormous role. And we don't use the Navier-Stokes equations in detail. We use what's called Darcy's law. So this is a connection between an extremely viscous lower layer and a totally inviscid upper layer. Next slide, please. Now, there's a lot of mathematics or algebra that I'm just not going to do. I'm just going to talk to you about the results. And it's reported in two papers by a very nice undergraduate worker with me, Joseph Weber, in the publications you see. Next, please. Now, the result for the dispersion relationship, the omega squared equals gk tang kh that I showed you before, is shown here in what's 49. I've stolen it from our publication. And there are a number of non-dimensional parameters. One is C, which is some indication of the wave frequency. Another is E, which is the ratio of the depth of the ocean to the total depth, capital D. The next is J, because this undergraduate student is called Joseph Weber, and I said he must have a non-dimensional parameter after him, which is K omega over nu, and tells you how important the viscosity of the lower layer is, and then a non-dimensionalization of the wave number, which is R. So going through the algebra, you get this very complicated or rather complicated relationship, which is complex in both senses of the word. A, it's complicated, and B, there are real and imaginary parts to it. Now, what that means is that you can determine R, which is the wave number, as some function of these parameters C, E, and J. Now, the important thing is, in the long wave limit, that is when KD is very much smaller than 1 because K is so small, what you find is that the result for KD squared is proportional to some concept which I've called H times C, this parameter on the top left. And what's most important and different from anything I've talked about before is that K is complex. The wave is damped by having to flow over the viscously dominated porous layer beneath it. Next slide, please. And this is a plot of the dispersion relationship for the water depth equal to the porous layer depth. And you see different values of the left-hand side, and it's equal to 0 where you have the white stars. And that's at K is plus or minus 0.76 plus 0.028 I. So what that says is there's definitely a horizontal wavelength, 0.76, that goes along with X, and some dissipation with X, which is the 0.28 I. So because it's e to the ikx, means it's e to the minus 0.28 X. So the waves are damped. Next slide, please. And thank you very much for this. So as I've said, the surface waves are damped by the porous layer. And interesting case, if you have a very deep porous layer, then K is purely imaginary, i.e. there's no propagation at all. In other words, if you put any waves over a very, very deep porous layer, you'll find that they'll be quickly damped. They won't propagate. Really important and quite different. Next slide, please. But now the Stokes drift, to see what's the effect on the Stokes drift. And whereas in the situation that Stokes investigated, there was a purely horizontal drift, in this case, there's a vertical drift as well. And you see in 47A and B, the horizontal Stokes drift in the fluid and the vertical Stokes drift in the fluid, and then 48A and B is in the lower layer. But what you see is exponential decay given by the imaginary part of Ki and a number of other constants. Next slide, please. Now, this shows what it looks like. For this case, I've taken the fluid depth and the porous media depth the same, and you see the fluid moves around and it gradually inches along in both cases. And now I'm sorry, there was a video that I was going to show you, but somehow that hasn't been included. Next slide, please. Thank you. This is again the result for a porous layer that's 3 times the depth of the ocean. And what you see that's most important is that there is a vertical component, quite different to what you would see if the porous layer wasn't there. Next slide, please. Just shows you the difference dependent upon the depth of the ocean. Let's look at the last shot, D equals 0.99. You can quite see that everything is horizontal. There's, of course, vertical motion because the particles go through ellipses, but the general flux is totally horizontal. On the other hand, if you look at the first slide, which I've already shown you, you see there's a vertical component. What that means is that there's water exchange between the coral and the ocean. That means biologically, the water will take biological stuff, little bacteria, little animals, up and down between the two. Next slide, please. This just shows how it will be damped with the distance. The far right slide, curve rather, shows you the horizontal drift speed, and you see there's a little break at a quarter of the way down because there's a difference in the ocean and in the coral layer. And as you go further and further into the coral layer, as I've shown by the arrow here, the velocity gets less and less because of the damping. And the second slide shows it when the ocean depth is effectively larger. Next slide, please. Look, let's move on to this. This is just another example. Next slide. This is really another example and shows you how the vertical Stokes drift, very different, a new idea, is different between the ocean and the porous media, as you see by the breaks. And you see how very, very small it is. How many knots are there? 5 knots. One when there's just a very thin porous medium. Next slide, please. Now, what I want to just present a little bit is some results when the porous medium is not of constant porosity. The simplest case, and there's still no doubt lots to be done, where you have a really high porosity at one level and a lower porosity at the other level. And that's very relevant to coral reefs where algae grow on the top parts of it and can cause difficulties. Let's go, next slide, please. This now shows the results, and you see the difference across the 2 or 3 regions of the horizontal velocity in the top slide and the vertical velocity in the bottom slide. And let me just remind you, if there was no porous medium, the vertical velocity would be 0. And that's what's new and interesting here. Next slide, please. Now, this work was really motivated by a wonderful talk given to me by, given to a lot of people, just not me, by Mimi Curl, a professor at biological oceanography at Berkeley. And she came to describe these experiments of her students, mainly students, a few postdocs in Hawaii. And I just thought it must be great fun standing on a coral reef like this and making measurements. And she mentioned during this seminar in Cambridge a number of times that there was motion, and she'd measured vertical and horizontal motions. And I came up to her later and said, "Excuse me, Mimi, if you're going to talk like this in Cambridge, you have to use the word Stokes drift." Stokes was here for almost his whole life. And she more or less said, "Who's Stokes? Who's Stokes?" So we started doing this work. Next slide, please. This shows some work by Mimi where she put dye into the coral and it came out into the ocean because it's taken along by the Stokes drift. Next slide, please. This is now a shot of the coral layer, and what you see is, and is interesting, is it's not flat. In my calculation, it's a totally flat top, and I know that's an approximation, but you have to crawl before you can run. And it's also considered horizontal in my calculations. I'm sure there is some variation with horizontal position, and we'll take that into account later. Unfortunately, the next slide, which I didn't put in until the last minute, I don't think you have it, shows you different sorts of corals from different parts in the world. And they are different. They do have different permeabilities and structures, and we have still to take that into account. But the work done on Hawaii is much better, much more voluminous than anywhere else. As some of you may hear, I have an Australian accent, and so I've desperately tried to get some data of the last year from the Great Barrier Reef. So far, nobody seems to want to give it to me. Next slide, please. Here's some photographs that Mimi took. She injects the dye into the reef, and the dye slowly flows out. And then when it gets into the ocean, because there are waves on top, it goes back and forth. Now, again, the work we've done has assumed that there is a wave of one frequency and one wavelength. In the ocean, there's a spectrum, of course, and that must play a role in the detail, as you'll see in a moment. But this proves that our idea that there's a vertical interchange is correct. And nobody had looked at that analytically or mathematically before. Next slide, please. This just shows you that the velocity varies somewhat with time. It's a sinusoidal aspect, but of course there are a number of frequencies, and you see in the lower graph, the power as a function of frequency. For relatively low frequencies, it's quite high, and then as you get higher frequencies, it decreases. And we'll do that in the future. Another undergraduate student. Next slide, please. These are some indications of the net flow that Mimi measured. You see in the ocean, it increases with the depth. It's smaller, just as we calculate, and you'd expect in the porous media, but Mimi had already measured the vertical interchange of 1.5 centimeters a second. This is the average measurements. Next slide, please. These are the maximum measurements showing you how important it can be. Right at the surface, it's as much as 12 centimeters a second, sorry, surface of the porous medium. So there's a vertical component there, and the horizontal component increases in the ocean, which is what you measured, just as Stokes himself had originally said, but he didn't take into account the vertical aspect, which is all important. Next slide, please, and important particularly for the biology. Now I'm going to say something which none of you must repeat, please. How do you work out the various parameters like the permeability and the porosity and the heterogeneity of the coral? Well, one way to do it is to take a large amount of coral and put it into a big beaker and measure the flow through if you put in fluid at a constant pressure. As it says in the bottom right, measure flux through coral as a function of pressure to determine permeability of homogeneous and isotropic. Now, why none of you must mention this is it's totally illegal to take coral away and take it into the lab. So this is, I could end up in jail. Well, I don't think so, but I could end up in trouble. Well, so could a lot of people. But this is what we did. Next slide, please. This is an example of the coral on Hawaii, and you see the regions through which the water flows and what it's like. Next slide, please. This is now the measurements. Of course, they're not constant, it varies, but here you see the variation in porosity from something like 0.35 to 0.5, with a rather significant variation in permeability, depending upon whether you put the big coral chunk in one way or upside down. There's no doubt some heterogeneity in that bit, and there'll be heterogeneity in all the bits, but we're doing the best we can. Next slide. Now, I find this data fascinating because this is our measurements for different amplitude waves. Sorry, this is our theory for different amplitude waves, relatively big yellow and relatively small blue. The height above the reef, what the horizontal drift velocity would be. Mimi measured this and got quite a few different values depending upon when and how she measured it, etc. And they were indicated by the crosses. What I find fascinating is the first referee's report, I'm ashamed to say, started with, well, this can't be a very good paper. One of the co-authors is an undergraduate, which A is stupid and B hurt the undergraduate, and C is irrelevant. Undergraduates, at least two I can think of, have written papers which have got them the Nobel Prize, so unfair. But what the referee also complained about is, gee, Curl's measurements have error bars with them. The theory has no error bars, so it can't be quite right. Well, of course, we could have put in error bars, but that would have been inappropriate. Next slide, please. But there's good agreement, as you see. So this is now a summary of the biological importance that you bring between the two regions, prey and oxygen, and a whole series of things can interact. It's very important, and none of the biologists had done this, really, to look at the important fluid mechanical interactions and how large they might be. So it is important biologically and has interesting fluid mechanical aspects, and we're going to continue that, and there are more applications that will be considered. Next slide, please. So this is now a summary, the take-home messages, that the Stokes drift in a high Reynolds number fluid like the ocean above a low Reynolds number porous layer has a vertical component, so there's an exchange between those two. This has important ramifications for both predator and prey biological species, the interchange, the ability to get food or to eat, or to get food to be eaten. Now, there's no doubt that this is but a first step. I'm sure that reefs are not homogeneous, which is what we've assumed, the same permeability. I'm sure, as I've already mentioned, they're not horizontal, but they have a slope. There's a variation in the top, but this is a very interesting, in my opinion, first go. I've been working on this for about a year, and I've tried to find out from people who ought to know what the differences are between the Great Barrier Reef and the Hawaiian corals and other corals. And so far, I've not been successful, I'm afraid. So the next slide. Oh, did I leave that out? Is there not another slide? What is this? How embarrassing. I may have cut it out a little bit in order to send to you.
It's 11 o'clock.
I'm sorry, yeah. In order to send it to make it to the right size, there was a photograph of Mimi Cole and Joseph Weber, and I'm sorry that that's not included. Well, Anton, that's the end of my presentation.
Thank you very much, Huppert. So, dear colleagues, now the session is open for questions. Please, if you have any questions, you can either switch on microphone or raise your hand. We can see it. And
I have a question. May I ask?
yes, please, Dr.
Hello,
Pushkin,
Huppert.
Thank you very much. Very nice lecture. I have a stupid question as usual. So, is there any relation between Stokes drift and the dispersion relation? So, for say shallow water and deep water, you have different dispersion relations. Will the Stokes drift be also different, and is it somehow related to dispersion relation?
Well, if I understand, well, the dispersion relationship is really telling you what's the relationship between the wave number and the wavelength of the wave, the wave number and the frequency of the wave as it goes along.
Mm-hmm.
So that's the fundamental, and if you like, first step. The second step is what is the particle motion, and that's different to the dispersion ratio.
Yeah, I understand that they're different, but is there any relation between them?
No, not directly.
Not directly. Okay, thank you.
But now, Vitaly, can I just say you've put a very good idea into my head. What a good question you asked, which is as follows. What about if the flow is turbulent? Everything that I've done so far has considered it to be laminar. And when you mentioned dispersion, the first thing I thought about was dispersion in a turbulent flow. And I'm sure you're right. The effects of wave breaking and the effect of turbulent motion in the oceans, but not in the porous media, would be something that's interesting to think about.
Okay, thank you very much.
Thank you.
Professor Huppert, and maybe I will ask, thank you, a very interesting lecture. And I think this is really a very difficult, challenging question about how the coral reefs interact with the waves in the sea. And I think in general, as I understand, this is kind of mutual process when waves, big waves can break the reefs from one hand side. From another hand side, reefs prevent the, for example, a laguna from the wave motion. The specific of the wave motion in the situation when there are reefs which are close to the surface, I believe this is quite different situation when, depending on the depth of the top points of the reefs. Can you comment somehow this?
Yes, as my calculations show, it does make a big difference what the depth of the coral reef is, whether it's really close to the surface or quite deep. But if I may extend your question a little bit, which you more or less hinted at, it's well known that coral reefs can protect land from ocean waves. But most important, an extreme case in some sense, is in the Boxing Day eruption, there were areas of Sri Lanka that were very badly hit by the tsunami, and other areas which were not so badly hit. And then a lovely Sri Lankan, actually, Joe Fernando, looked into it and found that there were areas of coral which were well known to be easy to steal. And there were coral thefts where there were large areas where there was no coral protecting Sri Lanka. So in those regions, the waves just went straight through and caused, as we know, terrible devastation and deaths around Sri Lanka. Some of the areas were protected by the coral. That's well known, and Joe has written about that. That leads to the next point, which is relevant to the calculations we've done. Maybe you could design not coral, but a porous media that would make the wave dissipate, just as we've calculated. So now the question which we're calculating and going to write up in the next few weeks, say, take the most extreme case, it's said off the west coast of Portugal and Spain, there are lots of volcanic islands where they have rock falls. And these rock falls turn out to be, or can be occasionally, quite bad. And people have said that could lead to the generation of a tsunami, which would head across the Atlantic and take over New York. Now, so the question is that you can't grow a coral layer to protect New York. I'll tell you that. But what you can do is calculate the best porous layer, best in the sense of most effective, and what height you would need and what porosity you would need to protect New York from these tsunamis. So as I say, we've started those calculations and we're going to write them up.
Okay, Huppert, thank you very much. I think this is really very interesting to get some ideas from nature to make this kind of defense for our cities. Okay, now let us once more thank Professor Huppert. Unfortunately, we can't well express it in the usual way right here, but I think everybody are very grateful.